You are probably familiar with the fact that if you take what seems like white light and you pass it through a prism or just some water, you get a spectrum of colors. We call those colors stereotypically red, orange, yellow, green, blue, indigo, and violet. You can remember that order by thinking of the mnemonic Roy Gregory Biv likes to wear tie-dye shirts, tie-dye rainbow-colored shirts. But what actually are we looking at when we look at this spectrum of colors? What this is a bunch of electromagnetic waves of various wavelengths arranged in order. So what seemed like a unified beam of light actually turned out to be composed of separate waves of different wavelengths, and they were bent by your piece of glass or your piece of water. And so as you can see, the violet color seems to have what are called shorter wavelengths. A wavelength is a distance between successive crests, while the red-orange colors have longer wavelengths, so the distance between successive crests is much longer. Okay? Instead of representing each of the individual waves like that, we can just represent them as a single wave. And here we have a long wavelength and a short wavelength. The important thing the IB is interested in your knowing here is the relationship between the frequency, the energy, and the wavelength of different waves. They don't care too much that you know exactly what an electromagnetic wave is, or that you can define it as a vibration of magnetic fields and all that fun stuff. All they care about is this relationship. So let's talk about it. So you have a long wavelength. It turns out that a long wavelength is correlated with a low frequency and energy, while a short wavelength is correlated with a high frequency and energy. Or not correlated. Correlated isn't the right word. Proportional to, you could think. Or connected to. What's the right word for that? Well, let's move on. Anyways, the important thing is let's try and find a way to get the intuition for this relationship. Okay? So imagine you're a surfer on the beach, say in Santa Monica. And on a specific day, it's really windy, and you notice that the difference, the distance between waves, between successive waves, is quite short. So a wave hits you, and then 3 seconds later, another wave hits you, and then another wave hits you, and another wave hits you, and on and on. You might say, wow, these waves are really high frequency, right? Or you might say the ocean is too high energy for me today, right? So you get that relationship intuitively. On the other end, imagine a non-windy day, okay? You're trying to surf, and you get one wave, and then 50 seconds later you get another wave, and then 50 seconds later another wave. You might say, wow, these are really low frequency waves, right? Long wavelength, low frequency, right? Or you might say the ocean is too low energy for me today. I don't feel like surfing, right? So it's a pretty intuitive relationship. You can remember that violet is the high energy end of the spectrum by remembering that mnemonic there, violent violet, okay? So the space between her sword waves is very short, but she's very energetic, right? Violent violet. Or you can think ultraviolent, which comes after violet. All right. Now, there's some important math notation that the IB might hold you responsible for to explain this relationship. We say that frequency is directly proportional, that's the symbol there, to energy, which means as one goes up, the other goes up as well. As frequency goes up, energy goes up. All right? High frequency, high energy. On the other hand, I'm going the other direction. On the other hand, as frequency goes up, wavelength goes down. The way to indicate that relationship mathematically is we put the symbol here for proportionality, but we put 1 over wavelength, okay? So as frequency goes up, wavelength seems to go down. And finally, energy is also inversely proportional to wavelength. So energy goes up, wavelength goes down, right? So high energy or high frequency waves tend to have a short distance between those successive crests. Here's a comprehension check for you. Which of the following statements is incorrect? Pause and think about it. Here is a clue. Sorry, I accidentally showed you the answer. Well, there's a clue. I'll draw the clue in. There's a clue for you. All right. And think about the answer. I'll give you 3 seconds. 1, 2, 3. There's your answer. Okay? Now that we have considered the visible part of the spectrum, we might ask, is that really all there is to it? Is that really all there is to the electromagnetic spectrum? Or are there things beyond the limits of human vision? Of course there are, because if not, I wouldn't be asking you this question. It turns out that the visible light part of the spectrum is just a small part of a much larger spectrum, and we can arrange that spectrum just as we've done with Roy G. Biv in order from low energy low energy to high energy at that end. All right, so let's look at the individual parts. We have radio waves, which are quite long wavelength, microwaves, then infrared, which are a bit longer than red, right? Ultraviolet, which are a bit shorter than violet, X-rays, and then gamma rays, right? And you should be intuitively familiar with the energy ordering of these. You should intuitively recognize that these are high energy waves and these are low energy waves, right? Gamma rays, for example, you might associate with nuclear accidents, like that one picture, the Chernobyl accident, which really decimated wildlife and killed lots of people as well. You know that X-rays, you shouldn't get too many of them, because eventually they do start to do your organs damage, right? We know that ultraviolet can be quite harmful to skin, so you want to put on sunscreen to protect yourself from that. We know that infrared is not that high energy. Infrared is released by warm bodies like this fox, or I don't know what that is. Is that a dog or a wolf? And we can visualize it with night vision goggles. So any sufficiently warm body will release significant amounts of infrared light. Microwaves are also low energy or long wavelength waves, but somehow we can cook with them. Why is that? Well, what's happening is the microwave is producing a high intensity of these low energy waves. And so the net effect is you can actually heat up things quite high. All right, so you can think the amplitude of the wave is increased. There's an interesting experiment where you can deduce the wavelength of a microwave using some cheese or some chocolate. I recommend this experiment. Radio waves are also pretty low energy. They pass through your head all the time when you have your phone on this side of your head and the satellite is over there, right? And they don't do you much damage. Here's a mnemonic to remember the order of these. Raging Martians invade Venus using X-ray guns. You don't actually need this mnemonic. I just like using it because you have your periodic table here. Not your periodic table, I mean, you have your electromagnetic spectrum in section 3 of your data booklet, okay? The last thing we will briefly talk about is the fact that although we've been thinking of light as a wave, it is also sometimes helpful to think of light as a particle, as tiny particles. We call these particles photons or wave packets. So tiny particles of waves, which have no mass, by the way. Very confusing. So a gamma ray photon will be a wave packet with a high frequency and high energy, while a radio wave photon is a wave packet with a low frequency or low energy and a high wavelength. Okay? All right, so let's do some comprehension checks again. Pause and think about this. I'll give you 3 seconds, then I'll show you a clue. 1, 2, 3. There's your clue. 1, 2, 3. There's your answer. Another one. Pause and think about it. In 3 seconds, I give you a clue. 1, 2, 3. Oh, there's a clue. In 3 seconds, I give you an answer. 1, 2, 3. There's your answer. And I think that's all I have for you. So I will see you in the next video.